Okay guys, what we have here is the serial speed test for our quadcopter command center. We had issues previously with the aero-quad software and our modifications sending information at more than 10 Hz. The issue being that the PC event handler would only read the first line because we were using the serial.readline function from the .NET library. This was okay during initial testing because of small volumes and low frequencies, meaning the event handler could trigger fast enough to clear the buffer. However, when sending multiple values of information, the buffer will fill. This is because the PC end will only read the first line. Over time, this causes the buffer to fill to an infinite value, hence infinite latency. The solution to this was to read the entire buffer and append it to an existing string. The string is then searched for line breaks and a for loop run to process all the received commands in one event. We then remove the process values from the string. A command may only be half sent by the time the event handler triggers, but this is okay, as it will be retained in the string and the rest of the value appended next time the buffer is read. In this test at low frequencies, you may notice the in buffer is always roughly 3 to 5 bytes. However, you also notice that when the speeds begin to increase, the buffer length grows. This shows by the time the event thread begins, many commands have been received. You should also see the processor clock speed and usage increase at high speeds due to the for loop run to process all our commands. In order to ensure there is no lag, a response button is available and will be tested over a range of test frequencies. At high frequencies, it is notable that this is not so stable. A check is run on every count value that the program receives, whether it is normal that when changing frequency or sometimes running a latency check, the incorrect count increases. So we'll start the test and we'll set the frequency to 1 Hz. Now try 10 Hz. We'll now try 100 Hz. $200. 500. We'll now do a response check. As you can see, most responses are coming through, as well as with very little latency, and here we have had an error. This, however, is at 500 Hz, which is way over what we need. If we go back to 100 Hz, which is the value at which the aero-quad, well, the max value that the aero-quad software returns values, we'll notice that the responses are mainly successful. So we'll return to 500 Hz. Let's try 750 Hz. After this frequency, you may notice the clock speed here will jump up every now and again. You should also notice now that the processor usage has also increased to deal with our commands. This is now at 1 gigahertz. Sorry, excuse me, 1 megahertz. Sometimes when setting the frequency at high speeds, the microcontroller will not receive the value properly and the set frequency button has to be pressed multiple times. I can now try at 1500 Hz. We'll now try 2000 Hertz. You should see by now that the processor is remaining at the higher clock speeds, and we're using roughly 20%. Try 3000 Hertz. Even at 3000 Hertz, we're getting some of our response values, and the latency is not bad either. (4000 Hertz). At this point, the frequency we have set, we don't think the microcontroller can actually exceed this value. We've not actually tested to see if the microcontroller is sending at 4000 Hertz, but we can safely assume that this is far faster than the 100 Hertz maximum which the aero-quad software will update our computer at. What I should also mention quickly is at 1000 Hertz, you should also notice, and you may have noticed before I pointed this out, but the read buffer size has grown from 5 to around 20. Now what we have requested is 4000 Hertz, but we think is at the limit of the microcontroller. You'll see that the read buffer size is roughly 48. Our max buffer size, or the limit that we have set, is 50. So whenever this is hit, this in buff max hit value will increase also.